Alright, in this video we're going to be covering the charging system. We're going to look at the components that make up the charging system, identify and test the parts inside the alternator, and get an understanding for rectification, the regulator, and the charging system indicator. First of all, looking at the components, we have the battery. Looking at this wiring diagram down here, batteries here, comes up to the electrical center with our fuses, over to the ignition switch, which is part of our circuit also. Looking on this side, first of all, comes through the indicator light. On some of the systems, the indicator light is a critical part of our charging system. If this light were to burn out, the regulator does not receive a wake-up signal. You actually lose your charging system because of this light going out or this fuse. This indicator light on some systems, the older systems in particular, was a crucial part of it. This signal over here is what the regulator is going to be using to monitor the battery voltage. And then this wire here is going to be the battery terminal, the heavier cable off the charging system. When you see the diodes like that, that's the output of the alternator. Looking inside the alternator, we have the rotor here, which is going to be our field coil or electromagnet. These three windings here are going to be our stator, and this is a Y-type stator. Inside of the alternator, we're going to be using electromagnetic induction. You have to make sure that you understand that. To understand the charging system, you have to understand electromagnetic induction. This is one of the places on the car that we want the electromagnetic induction. If a conductor passes through a magnetic field, it will induce a voltage into it, or if a magnetic field crosses by a conductor, it will induce a voltage into it. To control that, we're going to control the speed at which the conductor passes through. Primarily here, the higher the RPM, we're going to have more output from the alternator. The strength of the magnetic field, the number of conductors, and the distance between the two, those last two are going to be determined by the engineers that design the alternator. Taking a look at the alternator here, we have the housing, which is always going to be aluminum. We have a lot of heat that's generated inside of the alternator. We have to be able to get rid of that heat. They're going to have most of the time a fan on the front side, which it's kind of different from what you'd think. This actually pulls the air from the back of the alternator through to the front, even though from our radiator we have air pushing the opposite direction. There are some manufacturers that have mounted the alternator inside of the engine where it's going to use coolant to cool it down, which a liquid is going to conduct the heat away from there 4 times more efficiently than air will. The rotor, which is this piece here, has this part, which is our slip rings. This is our spinning electromagnet. The stator, which is all the way around the rotor, that's where we're going to induce the voltage into. This part over here, you can't see a real good look at it. This is your rectifier bridge, where we can convert the AC to DC. This one does have a regulator inside, which is behind here. And then we have our bearings, which most of the manufacturers have a roller bearing in the back, ball bearing in the front. Our wear items are primarily going to be the brushes, which we will take a look at those later, and then sometimes a bearing will go bad. Taking a look at the rotor first. Here's the rotor outside of the housing of the alternator. These are slip rings. Over here are the brushes in a brush holder. There's springs back behind here that are going to hold this tension. You can see this pin that's inside there. When you go to assemble it, you have to have that pin in there. This hole right there, that pin is going to stick out. This holds the brushes back. After you get the alternator all back together, everything's all lined up, tightened, then you pull this pin out and you listen for those 2 brushes to snap against there. Without something holding those brushes back, you're not going to be able to get the alternator back together. The 2 brushes right against the 2 slip rings. One brush is going to be positive, one brush is going to be negative. You can see from this one here that it goes to a contact there. What you can't really see is there's a contact from here that goes into right there. These are the 2 ends of the same wire. It's wound around inside here a whole bunch of times. As we run current through there, this is going to become an electromagnet. You're going to get a north pole on one side, a south pole on the other side. These pieces here is going to be north, south, north, south. It's going to be the equivalent of about 7 spinning magnets. Because it's electromagnet, they're going to be a fairly strong magnet. And that's what we're going to use to induce the voltage. Rotor is our spinning electromagnet. To test the rotor, you're going to use an ohm meter. 1 lead of the ohm meter on one slip ring, one lead on the other slip ring, and you're going to look for 2.5 to 5 ohms. Second test is going to be from one of the slip rings to the shaft. You're looking for a reading of OL. Next component is our stator. There's two types of stators that are used on the vehicle. First one we're going to look at is the Y-type stator. So here's the symbol for the Y-type stator, and you can see it's shaped like a Y. That's where the name comes from. This neutral junction right here is how you're going to identify a Y-type stator. There's a neutral junction right there. I tried to zoom in so you can see. Each one of these 3 wires comes up at this point right here, and they're crimped together. On this one down here, what the manufacturer is doing, they're trying to get a little more output from this Y-type stator by coming off of the neutral junction. That's the reason that this has 8 diodes instead of the typical 6 diodes. The other type, and this is the more common type that you're going to find on the newer alternators, this is a delta. The delta symbol there, these are wired in parallel. So in the alternator, it's always going to induce voltage into 2 of the windings at the same time. You can go back to this one. On this one, if I induce here and here, you can see that the windings are wired in series, which is going to give it a higher voltage potential. On the delta, they're wired in parallel, which is going to give you a higher amperage potential. It's going to be identified, no neutral junction. To test either one, the Y or the delta, you're going to check from one lead to the next. With an ohm meter, you're going to look for a real low reading, 0.1, 0.2. Then check another 2. Again, you're looking for the 0.1 to 0.2. Then you're going to check from any lead to the housing here, and you look for a reading of OL. A visual inspection is going to be part of it also. Make sure that the rotor hasn't rubbed against there, that you don't see bare spots where the insulation is gone. What I've typically seen is when the stator goes bad, these windings are in the 3 groups, and you'll see a third of them are darkened. Third component is going to be our rectifier bridge. When we produce electricity using an electromagnet or a magnet, we're going to produce AC voltage. We cannot charge a battery with AC voltage, therefore AC voltage is wrong. If you have something that's wrong, you have to rectify it. It is going to rectify or change our AC voltage to DC. These all 4 are the rectifier bridges. On this one here, you can see there's 1, 2, 3 diodes there, and then there's 3 diodes over here. Again, they have the aluminum, the heat sink. They're going to generate a lot of heat. The higher the output from the alternator, the more heat they're going to generate, so you will always find some sort of heat sink on there. Diodes will typically have about a 0.5 volt drop across them, which means there's resistance there, so they do generate the heat. This one over here looks a little bit different. Typically we have the 3 wires coming up from our stator. This one has, from one stator is going to have 3 connections here, from another stator would have another 3 over here. This rectifier bridge is actually designed for an alternator with 2 stators in it. To test the rectifier bridge, you're going to put your meter in the diode test position. On this one here, this metal piece right here, this tang that's folded over, there's another one from the other side that's underneath that, and then there's the 3 for each side. You're going to put one lead on this metal piece here, the other lead on the aluminum, meter in the diode test position. If you're in forward bias on the diode, you're going to have a reading between 400 and 700 millivolts. Then reverse your leads, you'll get a reading of OL. You're going to do that on all 6 diodes, so there's 2 tests on each diode, which means when testing the rectifier bridge, there's going to be a minimum of 12 tests. Going through it one more time. Rotor is a spinning electromagnet. You're going to test it with an ohm meter, slip ring to slip ring, 2.5 to 5 ohms, slip ring to shaft, OL. The stator, that's the part that's going to have voltage induced into it or produce the voltage, whichever way makes more sense to you to remember it. You're going to test with an ohm meter, test from your leads, 2 of the leads, the other 2 leads, looking for 0.1, 0.2 ohms, and then from any one of the leads to the housing, looking for OL. And this one, you can see the neutral junction pretty easy, so this is a Y-type stator. Rectifier bridge converts AC to DC, tested in the diode test position, forward bias 400 to 700 millivolts, reverse bias, OL. I've covered that now 2 times, 3 times, so if you're taking notes, this is the part that you want to remember. When you're working on a customer's vehicle comes in, the battery's not charging, you go through and you diagnose that it's the alternator is the problem. You're going to replace the alternator. If you're working on your own vehicle or a friend's vehicle, brushes are going to be the most likely component to wear out. You can normally pick up a set of brushes for less than 20 bucks rather than spending $150 on a new alternator or more. It's probably going to be worth it for yourself. It's not something you're going to do for a customer. By the time you pull the alternator apart, test the components, get it back together, you're going to be an hour, hour and a half, 2 hours into it, depending on the alternator. When you're $100+ an hour, you're going to be better off just to put a rebuilt or a new one back on there. Taking a look at how the alternator is going to work, and this is my explanation of how to do it. This winding right here, this is our electromagnet, this is our rotor. Here's the 2 slip rings. Here's our 2 brushes. One brush is going to battery voltage, the other brush is going to ground. We have current flowing through here. Start the engine up, this is going to spin, it's going to induce a voltage into our stator. For this explanation, I'm only going to be looking at these 2 windings. I'm going to ignore this. I'll come back at the end and talk about what's going to happen here. First of all, as the magnetic field's lined up, I'm going to induce a voltage into this winding and this winding. Current is going to flow from X to Y, which means I'm going to have 0 volts here, about 16 volts here, which means I have about 8 volts here. With no current flowing through this winding, that means I'm also going to have 8 volts here, the 16 volts here, and the 0 volts right here. Current's flowing, X to Y, 16 volts here. And this is my X to Y here, my positive voltage. When I get to 16 volts here, it can't go through this diode. It's in reverse bias, so current's going to flow through this diode. I'm going to drop about a half a volt, so I'm now going to be about 15.5 volts. This is my output from the alternator. It's going to go run all the accessories on the car, recharge the battery, come back to the engine, which is our ground. Alternator housing is bolted to the engine, so that's my ground, and it's going to come back here. Now with the 3 diodes, there's 16 volts on this side. There's only going to be about a half a volt left over. That can't come through this because there's a greater voltage on this side. There's 0 volts here. There's 8 volts here, so it can't come through this one or this one. It is going to come through this diode, and there's my complete circuit. This became the source of my voltage. The battery is now the load in the circuit. And for current to flow, it has to go from the source back to the source. There was our X to Y. Alternator, or the rotor, moves a little bit farther. Now we're going to induce voltage Y to X. 0 volts here, 16 volts here, still 8 volts here. Current is now flowing Y to X. This is our negative voltage. The difference between positive voltage and negative voltage is the direction the current flows. This was X to Y. This one is Y to X, negative voltage. This is now going to come over here, 16 volts here, 15.5 volts here. Run the accessories, recharge the battery, come back with about a half a volt here, 16 volts here, came back up, 0 volts here as we're flowed Y to X. That's our alternating current. Positive, negative, positive, negative. In the stator, we have AC voltage. Once it comes over here to the center of the rectifier bridge, the positive voltage will always flow to the right. The negative voltage is always going to come through our negative diodes. This positive voltage, when it came over here to the battery terminal, that's this voltage. Our negative voltage, which was the Y to X, came over here, went to the right. There's our negative voltage converted to a positive voltage. As it goes around, this is all positive voltage going across there, converting the AC into DC. Everything is positive. If you were to take a scope, hook it up to a battery, it would be flat line. Looking at this here, there's no flat line there. This is a whole lot of up and down. Here's where we have our third leg. This is going to be a 3-phase alternator. And here's my 3 phases. So the black was phase 1, the blue is phase 2, green is phase 3. And you can see as phase 1 is coming down, phase 2 comes up, as phase 2 is dropping off, phase 3 comes up, and then phase 1. And then we end up with this line across here, and all I have, which should be up there a little bit higher, is this ripple that's across there. And this ripple is going to act like an AC volts, and we're going to talk about that AC volts a little bit farther. Alternator is going to produce AC voltage. We're going to convert it to DC voltage, so instead of current flowing positive, negative, negative, positive, it's always going to be going the same direction. Hopefully that makes sense to you. You can read more in the book if that was hard to understand or came at you too quick. From the alternator, this is important for you to understand. So real simplified, here's my alternator. Here's my battery terminal on the alternator. This is going to come out and it's going to feed to my electrical center. Battery is going to connect up also. Fully charged battery is going to have 12.6 volts pushing this direction. If I have 14 volts coming out here, electricity, just like humans, wants to take the path of least resistance. So the output from the alternator is going to run all of the accessories first. This light bulb represents computers, motors, solenoids, relays, lights, everything on the car. It's going to run all of those. It's only what's left over is going to overcome the pressure from the battery and recharge the battery so current flows backwards through the battery to the housing of the alternator. For that reason, if you check your battery voltage with the engine running, if you have 13.5 volts or greater, your battery is being fully recharged. And that means that the alternator is running all the accessories and has enough left over to recharge the battery. That's the test you want to do. Back in the days of the VAT40, which we covered in the last video, with the starting system and the previous one with the battery, we had to know what the full output of the alternator is and then test to see if it put out within 10%. We don't need to do that. What you need to do is turn your accessories on the car. Rear defogger, blower on high. If it has a rear HVAC, turn the blower on there. If it has the butt warmers, turn those on. Turn all the electrical accessories on that you can. Then check your battery voltage. As long as the battery voltage is staying above 13.5 volts, the alternator is running all those accessories and it's recharging the battery. If the voltage goes above 15 volts, now you got a problem. You need to go and check that out. The second test you're going to do, besides checking your voltage at the battery, is you're going to take your AC voltmeter, red lead here, black lead to the housing, and you're going to look to see that this reading is less than 200 millivolts. If it goes greater than 200 millivolts, then that means there's a diode that's going bad or has already gone bad. There's your two tests to check the alternator, and this will tell you that the alternator is adequate for this vehicle. DC voltage, 13.5 to 15 volts at the battery. AC voltage at the alternator are less than 200 millivolts. Typically, you'll find it down closer to 50 millivolts. Voltage regulation, 1, controlled by RPM. However, you're not going to slow down your driving just because your battery got charged up. The second way of controlling it is by controlling the current through the rotor, which is our magnetic field. So when they talk about a field circuit, they're actually talking about current through the rotor. We're going to start off talking about electromechanical regulator, even though we haven't used those for 40 or 50 years. This is a good place to start because it's easy to understand. I have one winding right here. I have a second winding right here. In my drawing over here, here's my one winding. Here's the second winding. This resistor and this resistor are on the bottom side of this plate, so you can't see those. I have a single contact on this relay, and right there is a single contact. This one is a double contact, so there's a normally closed contact, normally open. You can see the top one, which is normally open, and you can just see the edge of the bottom one, which comes to this plate. So there's actually two contacts on this plate, top and bottom. The bottom one is normally closed. 4 terminals, and this was all the manufacturers. Asian, European, domestic. This was the type of regulator they were using. One terminal went to the field winding, which is the rotor. This one went to the rectifier bridge. This terminal here went to battery voltage, so it was hot at all times. And this fourth one, here's our indicator light. Just like that very first wiring diagram we looked at, this is going to be the ignition switch. Turn the key on, voltage is going to go through the light bulb. It's going to come to here, which this has a lot of resistance. It wouldn't actually turn the light bulb on, but there's going to be a little bit of current flowing. A very weak magnetic field, not enough to affect this switch. It's also going to come through our normally closed contact over here to our F terminal, which is the rotor. This light bulb grounds through the rotor. The light bulb's going to be on. This is what they call the exciter circuit. This small amount of current going through the rotor, you start it up, engine running. As the rotor is spinning, it's going to have a weak magnetic field, but it's enough to induce a voltage into the stator, and now the stator begins to have some output. This coming from the rectifier bridge, which is coming from the stator. Current begins to flow through this. It will energize this relay and pull this contact down. Now that this contact is closed, voltage is going to be applied from number 3 through the closed contact over to here, which this voltage goes to the light bulb, and so we just turned the light bulb off with opposing voltage. It has battery voltage from the ignition switch, and now it has battery voltage from this side. It also is going to come through this normally closed contact to the rotor. Our alternator is now full fielded. We're going to get as much output from that alternator as we can based upon RPM. Battery voltage continues to climb now. Battery's getting charged. As the battery voltage increases, the current through this winding increases. When it gets up high enough, it's going to pull this switch partway down. Now, the battery voltage is going to come through this resistor to the field winding. What we just did was we shut the alternator halfway off. If the battery voltage drops down because there's not enough output, then it'll go back to this. Battery voltage climbs, it'll come to here. If battery voltage continues to climb, it will then close that contact. Now the current through here comes to ground. We just shut the alternator off. We have the alternator off, halfway on, full fielded, and this our exciter circuit to initially start the alternator working. With this style of electromechanical voltage regulator, if you were to pull this cover off while the engine was running, you would actually hear a buzz coming from these contacts. They're opening and closing fast enough, it's not even a click, it would be a buzz. Each time that you shut the rotor off, magnetic field collapses and the points inside here burn. They had kits to be able to go through and repair these. You could do a roadside repair if your alternator quit working. We've gone completely away from that now. We're looking at controlling it on the power side of the circuit. Some of them are controlled on the ground side. We're going to look at now an electronic one. Now, this electronic one is not a computerized one. It just has electronic components, but there's no programming, there's no memory inside here. Physically, this is what it looks like. These 3 terminals right here are actually those 3 bolts right there, so it's inside of that. This dashed line right here is a regulator. You can see there's 2 terminals here. What is not so easy to see is where this lead comes in. There's another one. So we have 1, 2, there's a 3rd terminal here, a 4th terminal here, and a 5th terminal there. These are our 1 and 2 right here, and where these bolts come through, these are our 3 other terminals. This one here is ground. That's this one. This one here is coming to that diode trio, which is this right here, and we'll talk about the diode trio. This one is coming to our rotor or to our field winding. Now let's take a look at how this is going to work. These 2 switches here are the ignition switch. Close this, we have our indicator light, but they have this resistor in parallel. The reason for doing that is if the light bulb burns out with this resistor, now the alternator can still work, so we don't strand the customer. Voltage with the key on is going to be applied here. Diode trio is in reverse bias, so it can't go that direction. It can go here, which is going to go to our rotor. So our rotor is going to have voltage, but it's the voltage through the light bulb. When it comes back over here, it needs to go to ground. That diode's in forward bias, but there's more voltage on this side, so it can't go through there. It comes to this transistor. Now we need to know, is this transistor on or off? Looking at this transistor, you have to determine, is this a NPN or a PNP? So the PNP, the arrow is pointing in permanently. The NPN, the arrow is not pointing in. This one we can see the arrow is not pointing in. This top leg is the base. On an NPN, we need to put a positive voltage to the base in order to turn it on. We only need about 7/10 of a volt to turn this on. Our voltage that was applied here through the resistor, through this diode and forward bias, is going to put the voltage to the base. So this transistor is on, which provides our ground path for the rotor. I'm going to get rid of the ink that's on here. Ignition switch on. The light bulb and this resistor put our voltage here, which provides the voltage for the rotor. The rotor comes through this transistor, which is also turned on. This is our exciter circuit. Rotor begins to spin, induces a voltage into the stator. That voltage from the stator comes to our rectifier bridge, which also comes to this diode trio. The electronics in here can't handle AC voltage. This diode trio is going to make sure that only a positive voltage is coming to here. We have the output from the stator being applied here, which means our voltage is going this direction. Voltage applied to this side, voltage applied to that side, our indicator light goes off. Now with full voltage applied to our rotor, we're full fielded. Voltage is going to start climbing. Now we're going to look at this circuit here, this number 2, that comes to this one, which has 2 resistors wired in parallel, but this one is a variable resistor. Specifically, it's a thermistor. What this thermistor is going to do is going to allow a higher voltage when the engine is cold. If you're taking notes, write that down, a higher voltage when the engine is cold. The battery does not like to work when it's cold, so they put a higher voltage to it. You can see on a real cold morning, battery voltage may go as high as 17 volts. It will drop down fairly quickly. The point is that the regulators compensate for temperature by raising the voltage to help get the battery recharged. This voltage is going to come through here with a voltage drop. It's then going to come here, and we've got this diode in reverse bias. However, this is a Zener diode. The Zener diode is going to allow current to flow in reverse bias. Once it gets above a certain point, as battery voltage is increasing, we're going to apply voltage to the base of this transistor, which is also an NPN transistor. Now, pay attention to this. I've got a voltage here. When this one turns on, this voltage is now going to come through here to ground. As this one turns on, it's going to start turning this one off. This is using a transistor like a amplifier. It does not turn it on or off. It's variable. And in fact, it's infinitely variable. As transistor 2 begins to turn on, transistor 1 is going to be turning off. Each little bit that it turns off decreases the current flow, which decreases the magnetic field. So they're using transistor 2 to control transistor 1. Transistor 1 is controlling the field current. And that's how they're going to do this on these electronic ones. On the base of this transistor is a aluminum base, and you can see the aluminum through these vent holes right there. When you put these in where you have a surface of the flat aluminum to the aluminum, you need to put a thermal paste on there because they have to dissipate heat. This transistor right here is going to generate a lot of heat when we have this alternator mostly off. Heat is what kills electronic components, so we've got to be able to dissipate that heat. That's why you put a thermal paste on here. When you open up an alternator, when you see aluminum to aluminum surfaces together, you need to put a thin layer of thermal paste on there. Here's the bottom side of that. That's where you need to put the thermal paste, is on this flat surface here. These are all different styles of regulators. This was the electronic one. This was an external one, electronic also. When we get into these here, this is where we're now computerized. This one actually has a memory inside there that has a processor. It's able to control the light. On these newer ones where they're computer controlled, they can turn the light on if the regulator sees a problem inside of the alternator. If the voltage is too high, too low, we have the regulators that are doing much more now. This one was a Ford, and Ford called this an IAR, an internal alternator regulator, even though this regulator actually mounted to the outside. This one and this one go on the inside. There's your heat sink to try to dissipate that heat. This one had the heat sink on the bottom side, and brushes were part of this regulator assembly. Some of the regulators are outside of the computer, and then a few manufacturers actually put the regulator in the engine computer. From a technician standpoint, that's kind of nice because you can put a scan tool on there and you'll have 4 or 5 codes dealing just with the regulator. And you can see, hey, there's a code for an open field circuit. So you're going to check the wire between the computer and the alternator. If that wire is good, you already know, hey, one of the brushes has gone bad. You've got a pretty good idea of what's wrong inside there before you opened it up. When I have an alternator that's not working, I confirm that the problem is at the alternator. As I pull it apart, I can test all these components. When the regulator is internal, I can't test the regulator, so the regulator is really a process of elimination. I can test my rotor, my stator, my rectifier bridge. If those are all good, but it didn't work, regulator is where the problem is. First one we're looking at is the indicator light, which I will refer to, and I'm not the only one, refer to it as an idiot light. The reason I call it an idiot light is because it is not going to come on until you have a catastrophe. So the system has completely failed by the time that light has come on. It's not the best way to monitor what's going on with your charging system. The second one is an ammeter. If you're going to add an ammeter to a vehicle, here's an older ammeter. You can see discharge here, charge here. When you go to hook this up, it has to be hooked up between your electrical center and your battery. Because all you want to monitor is the voltage that's either going into or coming out of the battery. If this is on the side of discharge, that means the alternator is not keeping up with the loads and you're actually running off the battery. If it's over on the charge side, it means, hey, we're charging the battery. However, that doesn't tell you if the battery's good or bad. You can have a cell inside of the battery that's shorted. It's now getting the battery really hot, but all you can see is that, hey, this gauge is over here on the charge. The voltmeter, if our alternator is not charging the battery, the voltage is going to be low. If something's gone wrong with the regulator or with wiring somewhere and our voltage goes too high, we can see that here. The voltmeter is by far the best way to monitor this. Now, if you can just get yourself and your customer to look at that gauge every once in a while. The reality is there's only 2 gauges that people will watch. The first one is their fuel gauge. They're going to watch that one all the time. Then you're driving along, you see a cop, and you'll look at the speedometer. When you have a vehicle that the system is not charging, and I've come across this a few times, there was nothing wrong with the alternator, with the regulator. Electrically, the thing was good. What was happening was the belt was slipping. You get a little bit of water up in there, and that belt just slips, and it's because the belt was worn and or the tensioner had gone bad. I'll show you this belt here. This is the newer belt. And the newer belts, they don't crack. You can't judge a belt by how many cracks are in it. What you're going to judge by is the wear in here. And this is showing you the Gates tool. This is the Gates tool, which you can go onto the Gates website, jump through a few hoops that they have, and they will send you this tool. You're going to lay these grooves down in here and then try to wiggle this back and forth. If it'll wiggle back and forth, there's too much wear, the belt needs to be replaced. These belts typically last about 90,000 miles. When you go to take it off, most of them use the automatic tensioners like this. If you don't replace this tensioner, what you're saying is that this tensioner is going to be good for another 90,000 miles. This tensioner has a spring inside of here. It's gotten hot, cold, hot, cold. As the engine's running, it bounces back and forth a little bit, and I do not believe you can guarantee this for another 90,000 miles. So I am of the belief that when you change the belt, change the tensioner also. The other thing that I've seen, and I was working on this one Suburban, and I noticed when I was running it, doing some other tests, that the voltmeter showed low, which the voltmeter in the car, I don't put a whole lot of stock in that because they're not real accurate. But it was low enough that I decided to check it, and sure enough, the battery voltage was down about 13.2, 13.1, somewhere in there, with no loads on. I checked the voltage at the alternator, and the voltage at the alternator was just shy of 15 volts. I had an extreme voltage drop across that circuit. This is an example of something that you would find when you have that type of problem. Just because your charging system isn't working does not mean it is a bad alternator. need to check the belt, check the tensioner, check the wiring for voltage drops. That's it for this video. Hope this helped you to understand how the charging system works.